The deep belief network model then assumes that each sheet of Cortex is just made out of these units, which are either on or off, and it's not especially Cortex-like. It's Cortex-like in its connectivity between areas, but each unit is just Gibbs sampling nodes. The other paper that we can look at by Hawkins, as far as I know, is the first time anyone has really dug down into the layers of Cortex and given specific mappings for what each population of neurons is doing. So I was gobsmacked when I first saw this theory. In my own research, I started out as a cognitive scientist, and I figured this beige stuff was where it was all going to go, so I went off to do a PhD in machine learning, which was very rigorous, dry, mathematical stuff. And I've been longing for the day when the two fields came back together and all this mathematics from machine learning could be brought back into cognitive science, and these two parts of my own career could be put back together again. And I saw a very early version of this in a bookshop in Oxford, and I almost literally fell off my chair when I turned the page and saw what he was doing. He's not from academia. He was rejected for his PhD application, I think, in neuroscience, and he went off to Silicon Valley where he invented the Palm Pilot and made an enormous amount of money from it. He's not an academic in our regular sense of the word. He's got where he is by actually building something in machine learning that works, and he's proved his skills for real rather than just writing papers about it. And it's also allowed him to be able to say whatever the hell he wants. He started off with an overall idea for how this theory was going to work, and then he collaborated with George at Stanford. So the paper you read is by George and Hawkins. George was his PhD student, and it was George who's done the nitty-gritty of mapping the individual Bayesian equations under the overall guidance from Hawkins. The overall idea is called Hierarchical Temporal Memory, and it is about combining Bayesian networks with hidden Markov models. The hidden Markov model is one particular type of Bayes net, but if you think of your regular Bayes nets as being static, stationary pattern recognizers, think of those pattern recognizers themselves evolving over time in the Markov chain. So you're making inferences about this complex hierarchical state of the world now, but also conditioned on its previous state. So right from the start of this theory, he's thinking more in terms of video recognition than image recognition, because real perception does happen over time, which is often ignored by, say, vision researchers when they build these hierarchical models. It's ignored in the Hinton paper we just saw, but he's later started writing about temporals, restricted blocks from machines, to get into this same kind of area. This is the output of the Hawkins theory. This is what we're going to build up to. And you can see this looks a lot like the layers of Cortex you've seen in your Cortex lectures. The difference is that every node here is specified as doing something, and they're all coloured in different colours. They each have a very well-defined function. They're each computing the probability of something and passing messages to each other. And the theory is arrived at in a completely top-down way. So you start by saying, I want to have these Bayes nets that can evolve over time. What computations would I need to do? And we saw an early version of this in the Rao paper we looked at. How would you build a simple hidden Markov model out of neurons? You can think of this as extending the Rao idea to the whole hierarchical structure. So now it's a temporal series of hierarchical perfects. We've got the usual story, information coming into layer 4, fusing together, getting passed up to 2 and 3, getting mixed up across columns, and getting mixed up with information flowing down, this is prior information, and then coming out from layer 5 and layer 6. And these become the messages going downstairs and upstairs. Again, this is just to give you an example of the final network that we're going to build up to. This is the simplest example you could find. This is from this supplemental information from the paper. Here you've got an image with some feature extractors. So one feature here is looking for a line, an edge, and this feature is looking for a corner. So there's two features from the image. What happens is you have a hierarchy of these nodes, and the nodes now are quite complex. They're more complex than a regular Bayes net node because we have this temporal aspect as well as a spatial aspect. The story is, each node has a set of coincidence detectors down here. As the name suggests, they are firing when combination of features downstairs comes on. Those coincidences are then grouped into temporal sequences. So you might have a coincidence of, say, the corner and the edge happening at the same time. And then a little while later, you just have the edge. That's a temporal sequence of coincidence patterns. So here we've got a set of coincidences. Here we've got a set of Markov chains defined over the coincidences. So the coincidences are the observations going into your Markov chain. And then you compute the overall probability of one of the Markov chains existing relative to the others. So these Markov chains are rival interpretations of what's happening in the data below. So you have the explaining away effect between them. And the overall probability of these Markov chains, that gets passed up as a feature to the next level in the hierarchy. So these hierarchies, both over space and over time, when you're looking for coincidences, you're grouping a whole chunk of space together and making one feature out of lots of lower level features. But when you deal with the Markov chains, we're dealing with a chunk of time. So this node is representing 4 steps of time down below, as well as, in this case, 2 steps of space. As you move up, you're getting a coarser grain both spatially and temporally. So we can take that right up here. This node just has 2 possible states, and one is where it's generating one Markov chain here and the other Markov chain here, and in this one it's generating them the other way around. I think it's generating this Markov chain instead of this one. It can also send prior messages down as in BaseNet. So if this node has decided that Markov chain 1 is active, that will increase the probability of one of the states upstairs, and it will send a prior message down, and it will give you prior belief about which one of these Markov chains is active. You can recognize a lot of the Perl notation in here. It's very obviously influenced directly from Perl, so he's using the pi notation for priors, lambda for likelihoods. When you see the equations come out in this, it looks visually as if you've taken a hidden Markov model and Perl net and put them together. You see terms that have come from HTM theory, terms that have come from the Perl theory. So I'm going to go through his paper one computation at a time. We'll look at both the mathematical computation and how it's supposed to get neurally implemented. Again, using the Perl notation, we can think about the immediate likelihood. C here is a coincidence, and it's a coincidence at a single point in time. And here we're referring to all the evidence below the node only at that point in time. So for example, we could be at this immediate point in time, and this node is saying, what is the immediate likelihood of one of these coincidences from the Markov chains based only on evidence below me? This is extending the Perl notation. And notice he writes his pluses and minuses before the E here because we're going to end up with temporal notation as well. So the pluses and minuses mean is the evidence below or above me in the network. And then we're going to either have T or we're going to have 0 to T. 0 to T will mean all the evidence over time, like in the hidden Markov model notation. The hidden evidence term is using HTM notation with Perl network notation. So this is just the same update as you get in a regular BaseNet, because we haven't put time in yet. We're just saying what's the probability of one of these coincidences generating the data that is currently observed. So we've got some feature over here in this part of the image, maybe an edge, and some feature over here, maybe a corner in another part of the image. And this guy, C4, is looking for a combination of both of them. And we think of this coincidence as being a feature which is generating the data. This is all directed Bayesian networks. So we're dealing with likelihood terms. So what's the probability of all the evidence below me conditioned on me, just like in the Perl equations. And again, I think the Perl equations, this is done just by multiplying the likelihoods from each individual unit. So we know these children are independent of each other conditioned on parent. And so therefore we can just take the individual messages from them and multiply them together because of their independence with respect to parent. These are lambda messages. Then at each point in time, child J needs to send one of these, and that's going to be the probability of my state conditioned on each possible state up above me, just as in the Perl equation. This looks like cortical layer 4. This is all your sensory inputs coming in, and they're meeting each other, and they're not meeting anything coming down. They're only doing a likelihood computation. So the result of this is going to be a term, it's immediate in time, and it is not taking into account prior information in space either. There's a theory of layer 4. The next equation comes from the hidden Markov model side of the theory. Here we're saying what's the likelihood of Markov chain G given the current coincidence observation and the previously computed likelihood. So you've got to be a bit careful with the words for these things. It's not quite a prior because we're not taking account of any top-down spatial information, but we're taking account of all the previous bottom-up temporal evidence. You can't really call this a likelihood or a prior. It's using some prior information from time, but it isn't using the prior information from space. So it's just called lambda T of G, and it's defined in this way. Now it's defined as the evidence below me in the network, but from time 0 all the way up to time T. This is a whole set of temporal evidence. And it's just like we did Markov model equations, but written in this hybrid Perl style notation. And it turns out you can compute this by introducing variables just called alpha and defining them in this way. So in computer science, you can often compute answers for big problems by breaking them down into little problems, and then you have a function of all the little problems that adds up to the big problem. So these dynamic programming variables, they're kind of more complex than the thing you're trying to compute. What you're trying to compute is just a function of g, but we're introducing a function of both c and g. So we're saying, what's this quasi-likelihood in us being both in the g Markov chain and at state c within it? Remember, each Markov chain is defined over coincidences. So at each point in time, you're looking at one coincidence. So you're saying, what's the probability both that I'm in one of those Markov chains and that that chain is in state c? It's introduced as a mathematical device that helps us to compute the likelihood that we're. In particular, we can marginalize out over the c's. If we just want to get the quasi-likelihood of g, we can marginalize out these alphas over c to get back to lambda and g. These are nice to work with because you can apply the hidden Markov model update step. So this equation, second equation, is exactly the hidden Markov model update. This is the likelihood term in the hidden Markov model. So this is what we're observing now. And this is your update term. So again, we've got, this is effectively your prior. This is what alpha was at t minus 1. And then you have the transition. What's the probability of moving to the next state, given that you're in the g Markov chain? This is just the hidden Markov model update. So the observations are now these complex curl messages rather than just a simple likelihood observation. And to start this off, you need to put in an initial term, alpha 0, just to give you some, probably a flat starting quasi-likelihood. Think of how this could be introduced in a neural setting. We're maintaining these variables alpha of c and g. They're functions of the Markov chain and of a state within the Markov chain. We're updating them like a hidden Markov model. So Rao has already shown us how to do this. We can just take Rao's neural implementation and plug it in. But then we're doing this other step, we're marginalizing over the coincidence states within these Markov chains. So we take what Rao has done and then we put in this new population which is doing marginalization with Rao. Remember, Rao is only working with one Markov chain at a time. Here we're dealing with a whole set of computing Markov chains. We go back, remember each node has multiple Markov chains in it. So each of those has to have a little Rao-like population inside. And so this is how George and Hawkins set about implementing it. Here's the coincidence neurons that we had last time. Now, for each coincidence, we define a column, cortical column structure going up above it. And then every Markov chain we're interested in is going to transition between the coincidences. So all the blue nodes here form one Markov chain. So this is the temporal pattern of observing this coincidence, then this one, then going over here, then coming back over here. The nodes are laid out spatially in terms of coincidences, but then the Markov chains, they don't have a mapping from space to time. They can just be flicking around all over the place. So the green Markov chain is the rival Markov chain, which is looking for a different sequence of coincidences. Then remember, we need to marginalize out the coincidences just to give us these likelihoods of the Markov chains. So we introduce a new population up here. So this is computing your total likelihood that you're in this Markov chain, green Markov chain, and this is the total likelihood that you're in the blue Markov chain. In this case, there are two different populations of cells implementing two Markov chains. And in general, there could be a whole load of Markov chains, all implemented by the same kind of neuron, and then a separate population which is doing the marginalization. I remember we saw in Rao exactly what these nodes have to do, and it was quite complicated. If you take the full probabilistic version of Rao, they need to be taking logs of things and multiplying them and adding them. So it's pretty complex neurons there. Or you might want to split that functionality between several populations of neurons. Whereas these neurons are simple, they're just adding activations together. The next thing we need to do, as in the Perl system, is compute the posterior beliefs in each of these chains. So we just computed the likelihood of the chain. That's the probability of all the low-level evidence given that chain G is on. But now we want to say what is the total probability of chain G being on, and that involves putting in spatial prior information too. It turns out you can do this using exactly the same equations as likelihood, but with this one little pi added in. So don't be scared of this slide. This slide is identical to that slide, except what should happen is, yeah, we've added a pi. Everything else is just the same. So here we've defined variables beta, which have just the same semantics as alpha, except when we initialize them, now we do include the prior information. So these beta values are going to be your posterior beliefs about being in a particular chain at a particular coincidence state, but now including top-down information. This network is easy to understand as well. This is just a copy of the likelihood network, but now each of these chains has got a pi message going into it as well. At the beginning of the chain, you're receiving a top-down message. You think of all this as coming in through layer 1, and then both this network and the likelihood network are going to be happening in layers 2 and 3. The layers 2 and 3 now have 3 populations of slides. You've got, from the likelihood network, you've got this population, which is doing Markov chain likelihoods, and you've got this population, which are doing Markov chain overall likelihoods. And now you've got this population, which are doing Markov chain posteriors. There's a little bit of asymmetry in the mapping here, because you need to compute the marginals on those as well to get the beliefs. Now, the likelihood versions they've put in layers 2 and 3, but here they've taken these out and put them down in layer 5. Okay, so we're just going through the Perl equations here with an added temporal aspect. So we've computed the likelihood, we've computed the posterior, and remember the next thing we need to do is compute the messages that we send out to neighbouring areas. So we've used layer 4 to compute the likelihood, we've used layers 2 and 3 to get our posteriors. We can make use of neurons in the other layers to compute outgoing signal. What's the prior message? You want to say, what's the prior probability that your Markov chain is active given the state of mu? So let's say the node right at the top has decided it's in state 2, and state 2 involves Markov chain 1 being active down here. I want to send this prior message down to make this Markov chain active. From the point of view of the parent, that Markov chain is part of one of my coincidences. I'm a parent, I've got 3 spatial children. Each one of those children has to be in a particular state for one of my coincidences to be active. And the state of that child means which Markov chain is active in the child. So this is going to be a message that I send to Markov chain G. And all I do is I take all the coincidence patterns I have that involve that chain being on. I could be in many states myself, and some of those states are going to involve that Markov chain being on in one of my coincidences. So all I do is I just add up my beliefs in all of my Markov chains that involve the child Markov chain being on. So I here is just an indicator function. I'm going to sum out over all possible coincidences in the parent, and the coincidences which do involve this Markov chain are going to be summed up. My beliefs are going to be summed up. So effectively then you're just doing another summation network, and this indicator function is just telling you what's connected to what. You're saying one of my coincidence patterns includes this child, so therefore have a link adding these things together. These are my beliefs in each coincidence pattern, and then I just sum those beliefs up to get my pi message coming out. There's a problem with timing in the model. Over space you have a spatial hierarchy, so a large area of space can have several children in small areas of space. And at a particular time step, all the children send a message to the parent, and the parent sends a message to all the children, and everything's happy. But doing this over time is not so obvious, because you want nodes higher up in the hierarchy to explain series of events below them on each child. And so you only send messages between them when that whole series has completed. There's an asymmetry between space and time here. In a purely spatial net, every time step you're sending messages, but in a temporal net, you need to decide when the messages get sent. And so they postulate this additional timing circuit here. These are your belief neurons down in layer 5. And they've introduced a circuit which just keeps track of time. So every time one of these nodes fires, it adds something to an accumulator down here. When the accumulator reaches a certain value, so this is counting seconds, if you like. After so many seconds, this thing resets itself back to 0 and sends a spike signal back around to these nodes. So you're computing belief at each point in time, and then you're saying, am I at the time to send a message? And if it isn't time to send a message, then this node will just have 0 output. But if it is time to send a message, this node will relay the belief through the network, and it will also reset the timer ready to go on the next step. It seems like a bit of a hack, but it's required to make the HTM model work.
Why do you need to wait for each chain to finish? Why can't you, like with the hidden Markov model, all the information is included. Like everything from the past is in the message that you pass to the next node. Why can't you just send the message to that node?
It's just the way the messages are defined. Here, for example, you're dealing with all the evidence from 0 to E. And one of those evidence terms is the state of the whole Markov chain beneath me. So I need a single term that says what's the probability of the G Markov chain being on compared with all the other Markov chains. For me to update myself, I'm working in this discrete time domain where t equals 1, 2, 3, 4, whatever. So my time is the tick, and the input I need to do the computation is the total posterior probability of the Gth Markov chain having been active down below. I don't want the probability of that chain being active right now. I want the total probability that that was the right chain.
How do you know when a Markov chain finished?
Yeah, this is where it runs into problems. So the setup with these timing circuits, then they're each running on a little timer, and when it's got to the end of the sequence, that timing circuit will go off here and it will send a tick, give you a single output, and then reset itself. So you need this timer to be somehow synchronized with the durations of the Markov chains. It's tricky stuff. The
Markov chain is just like a repeating circuit.
Yeah, so every time it goes around, you send another tick coming out here.
I don't really understand what the Markov chain is doing.
In terms of this image then, I'm looking for these two coincidences. I have features, I've got an edge in the corner. Sorry, I'm looking for a whole bunch of coincidences. There's 6 possible coincidences. So this is just the edge. This is the edge and the corner. One of these, I think that's meant to be just the corner and so on. The Markov chain then is looking for a temporal sequence of those coincidences. So it's saying, have I seen an edge followed by a corner, followed by an edge a little bit higher up?
Right, okay. But there's one Markov chain looking for that particular sequence, and there's another one looking for
yeah,
backwards.
So this sequence is looking for motion. This is looking for a bar moving upwards.
Right.
See, that's a set of motion detecting neurons. Whereas this sequence is not so obvious what this is doing. It looks like this vertical bar is moving. There might be something going on with the horizontal bar as well. But they're kind of mini video sequences being looked out for. And each one of those sequences would be generated by a thing, a causal thing in the world. And that's what you're reporting going up to there. The way these equations have been set up is that I need that message to tell me the probability of that whole Markov chain being the right Markov chain. So if I sent messages at every point in global time, I'd be sending too many messages because all I need up here is the total probability of that chain. I don't want the probability of that chain at a whole load of different times being fused together, because that would be the wrong. It would be like counting all the evidence 20 times instead of just counting it once. So I have to wait until the chain is completed and then send the message going up. It's kind of weird then, you think, as you go up the hierarchy, these times get longer and longer. So this theory is saying when you get right to the top of Cortex, you might have a 1 second timing circuit. It's looking for these very long temporal patterns. He writes a lot about music in his examples. You could have a part of Cortex looking for a particular riff, say the musical equivalent of a grandmother herself. But you would have to wait until the 5 seconds, whatever, for that riff to play has elapsed before you can do anything. So you need these really long timing loops as you get higher up. As far as I know, there's no biological evidence for this, but it's something you have to postulate to make the HTM model work. So that's a complete set of equations. There's a likelihood computation in that 4. If you're computing 2 sets of Markov chains in layers 2 and 3 for likelihoods and posteriors, marginalizing them, and sending information down to layers 5 and 6 to compute messages going up and down the network. So he's built this. The other thing about Jeff Hawkins is that he's doing his research as a commercial enterprise, but he wants to sell this to people to do real AI stuff, like machine vision. This is an example of the HTM just running as a piece of AI, not necessarily as a neural model. But here we've got visual inputs going in. We've got, these are layers of the network that are pulling out features. So we've got cells responding basically to edges and then to kind of larger scale features, like these curves and these lines. And then he's trained it to do classification. So this is saying what's the probability of these objects, and the probability of a car is the highest. But as with Hinton, he's got some flashy examples. And again, as with Hinton, they'd be much more believable if they'd been done by someone independently of the guys proposing the theory. That's why we need people to do MSc projects. Getting back to Cortex, then we can put all the circuits back together, and this produces the big total mess we saw at the beginning, except now we know what it all means. So we've got information flowing up to layer 4. This is doing the immediate likelihood computation, probability of all the data beneath me, given that I'm in one of these coincidence states. So layer 2 and 3 is where most of the action happens. You have, there is some color coding in here, I can't quite remember what it is. There are two different processes going on. There's the Markov chains computing in likelihood and Markov chains computing in Pistorius, and each of the nodes Markov chains is instantiated in both of those waves there. And you also have cells, I think this purple cell is one of the marginalization nodes, so it's saying for all the nodes in the likelihood Markov chain, sum them up and give me a total likelihood that that is the right Markov chain. And similarly, when we go down, they're saying what is the total relief. And in layer 5, we're doing this timing circuit. So you have a second population of nodes which are keeping track of the cumulative time and then sending a feedback signal around coming back when it's time to send that. We can simplify it out by looking at a simple column like this and see all the individual populations more clearly. So again, here's layer 4, probability of evidence below me. And it passes up into layers 2 and 3, and we compute these alpha terms, which are the probability of all the evidence below me from the beginning of my chain time up to time t. So this is where the reset signal is getting used. All the evidence since the chain cycle started, and it's getting fused with all the previous temporal prior information. You need to plug in this hardware prior to get that chain going. The other circuit in layer 2 and 3 is the beta circuit, which looks exactly the same as the alpha circuit, except remember it has that extra little pi term there. And then we go down 5 and 6, and we're computing message to send down the network, which is one using that indicator function, and sending out the belief sorts individual coincidence. So they have 8 equations combining 12 Bayesian network theory with hidden multiplier theory, and it's tempting to give you a complete theory of how the cut from our perspective.